All right, welcome to your last lecture of the season. I'm glad to see that you all make it, all survived so far. So next week is finals, right? So we won't have any lecture next week to give you the maximum time you need to do your finals. But we do nevertheless have a bonus lab on Deutsch algorithm, and today we're gonna talk about that. So if you can come, please come. And this lab does not require any report. So you just come and try to see what it is like, and you earn 5 points for just participation. Yeah.
Do we meet here at the same time? Or?
Oh, that's a good idea. That's a good question. I guess no. I guess we'll just meet in the optics lab at 2:30, and you can start immediately. I will have Elon prepare everything beforehand.
Don't you want to explain it first at this class?
That's what I'm gonna do now.
Oh, good. But these are usually the theory class.
No, we're gonna.
Instruction.
It's called optical implementation.
I see. Okay.
Yeah. Sure. There are specific steps you need. Like for example, you need to use liquid crystal to control the wave play. Yeah. But I will try to have Elon set it up as complete as possible, so you won't have to do much alignment during the lab session. You can just enjoy taking your data. Okay. Yeah. All right. So Deutsch algorithm. Who remember what that is? Yeah, you missed the class last week, but we have a video. You can review after if you want. But basically, Deutsch algorithm is something that involves, or remember, 4 legs, right? So this is a quantum processor or quantum function, and the Deutsch algorithm is having an H, a Hadamard gate on a 2 input port, and a Hadamard gate on 1 output port, and that's all. And also, especially a 1 input. Okay. So, and then of course a detection here. Actually, this is part of the implementation too. You detect only 1 port. You detect here. All right. And you detect the same state. Sorry. My bad. I should put blue. Where's blue? Eden, could you get blue? Thank you. And I need red too. 2 red. So 2 red, 2 blue. Thank you. So if you input 0 and you measure 0, that means your constant is you have a constant function. So any input you put into this function, which is this, will give you the same result. Okay? But if you measured not 0, you have measured a changed state on the x qubit, on the first qubit. So in other words, if you measure a flip, that means you don't have a constant, you have a balanced. So each one take a value, either 0, 1 or 1, 0. Right? So that's just Deutsch algorithm in a nutshell. Okay, cool. Now, so last week we spent like 3 hours talking about it. And now we're gonna see how we're gonna do this experimentally using optics. All right, so first we need to define some gates, right? How do we realize Hadamard gate? How do we realize, actually there's no other gates. Yeah. How do we make gates in optics. So that's the first thing I want to go over, and it's not trivial. And then we will go straight to Hadamard gate. No, sorry, to Deutsch algorithm. So first thing is how do you do an I should say that in optics it is customary to have, if you want to have a two qubit state. If you want to build a 2 qubit state in optics, okay? So optical 2 qubit state. Then this is what we do. We make the path going horizontal with regard to a beam splitter. So the horizontal port, the horizontal lines are called, I think, 0. No, sorry. This is called 1. Okay? And this is called 0. So we use path. I mean, it's kind of trivial, but nevertheless, we use path to encode the first qubit. So path, we call it X, the first qubit. So first qubit, 2 qubit state, right? And at second state, we use polarization. Yeah? So and for polarization, we call horizontal. Again, horizontal is 1. And vertical is 2. Sorry, not 2, 0. Yep. Okay. I guess I could give this a name called A and B. A and B. Right. Yeah. So A and B. Horizontal path is 1. Vertical path is 0. Horizontal polarization is 1. Vertical polarization is 0. Yep. So that's how we build a. This is called a 2-rail. Yeah. It's called 2-rail mainly because the path, they are 2, horizontal and vertical, and they are like orthogonal. So this is called a 2-rail construction. 2-rail. All right. So now we need to figure out how to make gates with this qubit. So we have 1 qubit. First qubit is a path qubit, and the second qubit is a polarization qubit. We need to figure out how to make them like flip or make them into a superposition in exactly the same way we defined previously in quantum gates. Okay, so let's start with polarization. Right. So for polarization, we use a halfway plane to do many things. One of the simplest things we can do is flipping the qubit, right? So H to V, V to H. Okay. So how does halfway plane work? If you want to turn a vertical polarization into a horizontal one, like you want to do this, notice this is the direction of the E field. If the E field flip like this, that's a pi phase change. So we call this V and this minus V. Okay, so we have a distinction here. All right. So if you want to flip it to here, so as you can see, this is minus h, right? So if you want to do it this way without imposing an additional phase of pi, what do? Anybody know how to turn a polarization with half wave plate? Do you know? No? Do you know?
There are also quarter plates.
Yes, but we're not using quarter wave plate. We're using half wave plate right now. I won't explain how wave plate works. They are basically phase retarders. But the effect is, so if this is, it's something called optics. So wave plate is basically a birefringent material, okay? Like our BBO. When you have polarization aligned with its optical axis, you have the wave travel faster. It's called extraordinary. And maybe faster. Yeah, the wave travel faster because it's also called fast axis. If you have, so usually in a birefringent crystal, you have two axes. One is called ordinary, one is called extraordinary. This is called slow, this is called fast, because wave travel faster. The index of refraction is smaller here along E, along this direction, and the index of refraction is larger along the O direction. So this is called slow, this is called fast. Okay? And this is also called optical axis. Okay? So if you have, I'm not explaining it. So if you have wave that just go along the optic axis, it travels faster. If you have wave that do this, it travels slower. But if you have wave that has component on both, right? Then the two components will travel at different speed. And the phase delay between the two depends on the thickness of your retarder, of your wave plate. And you can design the wave plate to be at certain thickness so that the retardation between these two is 90 degrees. Over the phase leg between these two is 90 degrees. That's not, not 90 degrees. 180 degrees. So pi. So in that case, you will have, the other, your input is this, but when you come out, it is like this. And then, so you will rotate this whole thing by 90 degrees. Okay? Okay, so half wave plate is a pi. So because the full wave is 2 pi, so half wave plate is pi. So when you do half wave plate, you are rotating by 90 degrees. Okay? So that's basically generally how it works. And the rule is, the general rule is if you have theta, so the theta rule is this. If you have theta angle with respect to the to the optical axis, then your rotation is towards the axis by 2 pi, 2 theta. Okay, so that's how half wave plate work. That's how it works. So you can imagine if I want to have V flip to H, what should the theta be? According to my definition, 45. Yeah, because I want this to be 90. So this must be 45. Okay, so you see on the half wave plate at 45 degrees give you an X gate. Yeah, so V goes to H. How about H? How about H? So from this diagram, you can see that this is also the angle between the polarization and the axis is also 45, right? So if I apply this to a H state, it will flip it. It will turn it towards. It will turn it towards the axis, optic axis by 45 by also 2 theta, which is 90 degree. Optic axis. I think it's called optic axis. Yeah. So this is called X gate. Yep. The other possibility is to put where's my block? The other possibility is to put it at 25 degree. And what would this do? What would this do? 45. And what is 45? So let's call it phi, right? 2 theta is 45. Let me just call it this. How do I write it? How do I write this state in the H and V base? Do you know? Really? Oh, come on. Are you supposed to not know? Hey guys, how do I write this state in the H and V base? Second?
1 over 2h plus 1 over 2.
1 over 2h plus 1 over 2v. Yes?
Because that has to be unity.
Of course.
Oh, okay. Then it's square root 2 over 2.
Yeah, exactly. Yeah, so generally, the state in this spaces is sorry. Okay. Let me just say that this is, if I just call this phi, is phi, okay? This will be cosine according to this notation. This will be yeah. Oh, sorry. Yeah, and in terms of the angle of the polarizer, no, sorry, the halfway plane, it is this. Yes? Okay, so this is very much like the block vector, right? The block representation. 0, 1, with this half angle in front. All right, so that's this. Good. How about H? Maybe I should just put H in blue. Let me put H in blue. What would H do? This is harder. I'm gonna get a smaller one. Are you smart? Are you smart? Nobody wants to be smart at this moment. She's looking away. Are you smart? No? Okay, yeah. Try it. How much rotation will I get? For how much? Negative 45. Negative 45. So I will get to this same state from V, but I'm rotating H.
Yeah, I mean orthogonal to the.
So here, 45. Why?
This calculator.
Oh. Do you agree?
Can you repeat the question?
The question is, if I am starting with H, and this is my optic axis, what would this or configuration do to this state? How will you rotate? Clockwise or counterclockwise?
Again.
The question is, if I have my halfway plane orientation like this, 22.5 degree against the vertical, then what would this configuration do to my H polarization? How would this turn? Clockwise or counterclockwise? That's the first question you need to answer. Raise your hand if you think it's clockwise. Clockwise? Clockwise? We have 2 votes. How about you guys? Raise your hand if you think it's counterclockwise. 1 vote. How about you?
Isn't it the same?
Counterclockwise is this. Clockwise is this. How can it be the same?
Like the rotate degree of rotate.
Well, you first need to decide the direction of a rotation, and then you decide how much you will rotate, right?
No, clockwise is
All right. So, are you voting for clockwise or counterclockwise?
I still think it is the same. Can I think
Then just choose one.
just reflect?
What? Reflect.
Reflect.
No, you're going like this. Okay, you're going like this.
Yeah.
Behind the board, when the laser beam exit the wave plane, does the polarization rotate this way or this way? Clockwise or counterclockwise? Remember, these two are not the same. Even though they are the same polarization classically, they are not the same in terms of our qubit definition, right? If I go from here to here, there's a pi phase. So what I'm doing now is to rotate it without adding any additional phase. What do you think? Tim? Clockwise or counterclockwise?
No idea.
You need to make a choice. What do you think? Counterclockwise. So we have 2 votes for clockwise, 2 votes for counterclockwise, and 2 people who are still in furious debate. All right. Let me remind you again what I just said 10 minutes ago. Pay attention to this. The effect of a half-wave play, or any wave play actually, is to rotate your polarization towards the optic axis. So if the optic axis is this, and your polarization is this, you are rotate towards the optic axis. Okay? Toward it. So if you are here in H, you go that way. If you are V, you go this way.
I mean, you rotate clockwise by 90 degrees, you get the same. If you rotate anti-clockwise by 107 degrees, you don't need the same.
True, but my definition of so in terms of my definition of theta, so in this notation,
In the theta.
yeah, you need to define in a self-consistent way. Okay, I understand it's equivalent, but you need to define it in a self-consistent way. So in terms of theta, okay. All right. So anyway, so here, since the optic axis is here, it will rotate towards it. So that's counterclockwise. Okay, and by how much? That's the question. By how much? What is the angle between H and the optic axis? Yes, 67. Yeah? So you will do twice. You'll do twice. Okay? 67.5 times 2 is 135. Yeah? So you're right. It is indeed at this position. It is indeed at this position. Okay? Let me just call it phi h. Okay? So h will go to 175 degree, and that will phi h, and phi h is, let me just say for some time, phi h is minus, wait, let me just write this in appropriate order. So 1/2, because we have h defined as 1, right? So we write h later. So we write v first and h later. In the same way, here we have v minus h. Okay? So you see, this is 1 going to 0, 1. And this is 0 going to 0 plus 1. Yeah? This is Hadamard gate. Yeah? So you have V, you have H. Okay? So this is Hadamard gate. All right. So let me add to here. H halfway plane at 22.5 degree angle with respect to the vertical axis give you Hadamard gate. Hadamard gate. And Hadamard gate turns V to the symmetrical superposition and turns H, which is 1, to anti-symmetrical superposition. Yep. Okay. Okay, great. So these are the two gates we can use, we can do with for polarization. And that's all we're gonna need for this experiment: an X gate and a Hadamard gate. Okay. How about the path? So we got this, the polarization. We know how to do Hadamard gate. We don't know how to do X gate. How about path? We need to have, by the way, the flipping, the X gate here is used here. You see, because the Y qubit will get flipped or not, depending on the function of X, right? So if you want to control what the flipping of the Y qubit, you need to have X gate. Okay. And and yes, and so we got this too, Hadamard gate and X gate for polarization qubit. How about Hadamard gate for the path qubit? This one is trickier. Actually, very hard. And by the way, in the experiment, you're supposed to use the single photon state. But since the single photon state and the alignment laser plus excicon, they are aligned, right? So you can simply by just turn on the alignment laser and replace the BBO with excicon to use alignment laser to do this experiment and see if you get the same result and see if single photon state is necessary or not. Okay, I think that will be nice. But right now I'm gonna just focus on single photon state. So for single photon state, we have this operator rules for. Ian, can I get a black, one more black pen? I have only one black pen. Thank you. Or two black pen would be good too. And everybody remember this? This is the beam splitter, right? And 1, 2, and 3, and 4, and 0. So this is the annihilation operator. Okay? And there are two possible there are two common possibilities with the beam splitter. One possibility is the beam splitter imposed a pi over 2 phase on all reflected beams on both sides. So in that case, you will have this, and you will have this. Yep. Okay. And if you call this the horizontal one, I think that's our convention, right? Yeah, call horizontal one. Then it writes like this. Yeah, okay. So this is 0, this is 1. 1, this is 0. Okay. I1, 1I. Thanks. 0 is the horizontal. Okay. Yeah. So this is a beam splitter with a pi/2 phase shift on all reflected beam. There's another one with 0, so no phase shift. In this case, I'm gonna just write it. And in this case, it is this is B is 2, 1. Oh, here. Oh, by the way, here there's a 1/2. In this case, you have so that means the horizontal one. This one has a pi phase shift on this guy, but this one doesn't have any phase shift. Okay, this is constructed this way so that it will satisfy the photon commutation relation. And it also, so physically, the physical significance of it is energy conservation and time reversal. It's all very complex, but just remember that there are two possibilities. One is with a complex number, and the other is without complex number. With a complex number, it is symmetrical. So you have I phase on all reflected beam. But with this minus pi phase shift, you have actually 0 phase shift. You have minus on only one port, okay? So 3 will have a minus from this port, and the rest is not. So this reflection doesn't have a minus sign. Okay. For the optical implementation of Hadamard gate, we need to use this type of beam splitter. Okay.
Two different kinds of beam.
Sorry.
Is there two different kind of beam splitter?
Yeah. I think this depends on your coding. Yeah, it's quite involved. All right. I see that it is 3. Oh, no, it's not 1 hour yet, so I can finish this. Okay. So just want to say that. So see, I'm doing this without derivation because derivation will take super long, and it's not very useful in my opinion. So if we give the path, different names instead of using, so this is from the textbook, okay? But in our discussion, we will just give them different names, and we call this A, and this is B, and this is D, and this is C. Okay, now comes a very difficult, really difficult question. And I'll probably give you 1 point. I guess I could give you 1 point bonus if you can answer this question. Okay, so there's a prize for this. All right, are you ready? Yeah. Okay, cool. If I flip this, flip the direction, so I still call this D, C, and D, okay? If I flip the direction of my beam splitter, okay, and I still call this, so my notation is not changed. I call the horizontal output port A, yeah? The vertical output port B, horizontal input port C, or vertical input port D. If I keep my convention, but I simply flip my beam splitter by 90 degrees, okay?
Why did you change B and D to?
Do I? Oh, cool, crap. Do I change B and D? Yeah, I guess I do. Oh, right. So you're right. Let me do this again. Oh, no. Because see, this is the input. D is vertical input, and C is horizontal input. Okay, so according to this definition, yes, of course, I'm gonna put my D here because this is the vertical input. This is the horizontal, and this is the horizontal input. Understand? All right, so pay attention, there's a prize. So I'm doing the hard part for you. This is the hard part. Believe it or not, this is really hard. Okay, I'm doing the hard part for you. So what you need to do now is to tell me how does B return in the state of C and D, and A return in the state of C and D. So the two output state, how are they related to the two input state? Got it? If you can figure that out, then you can understand the transformation that this beam splitter imposed to the states. Okay. I will give you 5 minutes for break and to think. Don't talk to each other. There's only one prize, only 1 point, okay, for one person. So I cannot split it by, I cannot do like 0.5. But don't talk to each other, just keep it to yourself, and we'll reconvene in 5 minutes. Sorry?
Whereas how is there a negative sign?
I don't know.
Okay.
I don't know. Well, like really, I don't know because I told you that it is related to some coding stuff. But the entire the full derivation, I don't know. All I know is that this is what is required to keep energy conservation work and communication work. So you just need to stick with this information that you have.
And try to figure it out.
Right. It's possible. This much space to use. So we can have maybe host. Well, it's not smart to put your answer there for everybody to see, right? So we have like 4 spots. So we can have 4 people come up and write down the answer if you want. So first come, first serve. Who wants to write an answer? If you write your answer here, there's a chance for you to win the prize. If you don't, then no prize. Okay, who wants to try? You can pass, that's okay. That's all right. Life is not about competition. It's all about chill and sit in your chair and drink beer and do nothing. Yes, that's the meaning of life. So yeah, I don't need to stress. That's okay. You absolutely don't have to come up. You really don't need to do it.
How should I write my answer? Should I define?
Write down your answer as A and B. How do they combine? How are they related to C and D? Okay, so that's basic. You want to come up? There's one more spot. Well, you know what? Write your answer here. This is a spot for you. All right, cool. Thank you very much. Thank you all very much. Okay, I want to just say one thing quickly. Right now, we're using this type of bin splitter, right? I thought I was clear that we use this type of bin splitter. Okay, so this is what we have, and there is no I. There'll be no I. Okay, so I'm sorry. So all the answers that are with I. Would you mind telling me what this is? This is cosine pi over 2. This is I. Is this I? It's really hard for me to read this. It looks like cosine pi over 2, which is 0.
Yeah.
So this is 0. This is 0. Correct? Is that what you meant? Yeah. Okay, thank you. All right, so all the R with I are out. Okay, now we have 0, 1, and 1, 1. Okay, thank you. All right, so the answer is, to understand how this works, we need to go back to here and replace this with our notation, which is pretty easy. That's just this minus D plus C, right? So I'm just replacing 3 by A, 0 by D, and C by 1 by C, okay? And B is, I'm sorry, of course, there should be, over 2, don't forget that, but that doesn't really matter. B is D plus C. Okay. All right. So here, what do we do? Here, the horizontal output in relation to the horizontal input and horizontal vertical input, it is still, the phase relationship still remains. So this is this. This is plus. Okay, and B, all the relative phase relationship is the same between the input and output. Okay, so this is just plus, plus. Yep. All right.
So they are the same, you mean?
They're the same. They're the same as this. It doesn't matter how you turn, as long as you define your input port correctly. Okay, so don't go with the position. Don't define this as D. You go with vertical input. Okay, see what I'm saying? So this is the hard part.
Vertical is this
This direction is the vertical. Okay, this direction is the horizontal.
so the
With regard to the optical table, this is horizontal. Yeah, this is vertical, normal to the optical table. Okay, and this is parallel to all.
This is table and the line.
Oh, you're right. I'm sorry. Yeah. Sorry. With regard to the beam splitter, not the optical table. Okay. Yeah. You define. Anyway. If your table is like this and your beam splitter looks like this, then I will define this as horizontal. And this is vertical. I know it's all very confusing. It all has to do with the beam splitter. Like normal to the table?
Turn my head.
I know, I understand. But I would just say that this is the transformation assigned to this particular beam splitter. Okay, and if it's like this, then however you turn it, you just stick with this relationship between input and output state. Okay. All right. Let me continue because I am lagging. I want to say that so again, let me write it down like this. We define the vertical at 0. So this is 0. And this is 1, right? Yep. So in the matrix we write it like this. Okay? And C is 1. CD. Yep. Okay. So this is according to this relation. Okay, I want to tell you one thing, that this is not a Hadamard gate. Okay? This is close to a Hadamard gate, but it's not. Yes?
Yes, I have a question with when the psi is higher over the reflection returns will edit out the image. Then, but for the psi is put the visual from your side, then why here the reflection returns from A, it got minus, and but for B, it didn't get minus, turn up this reflection.
Right.
Yes, there's no problem.
So yes, it is asymmetrical. Correct. Asymmetrical. So this is a symmetrical configuration. Symmetrical, right? This is asymmetrical. That means it seems from this formalism, it seems like both the two sides of the coding. I would say from here I would interpret this as no, actually. All right, the complete matrix, the complete beam splitter matrix is this, and this is in the one of the book in the syllabus in the reference by Jerry and Knight. Okay, the third edition. No, the second edition. A2, A2, A3. This is the complete. I think this is cosine. This is sine. And this is cosine. And this is sine. 0 and 1. Okay. Okay, you can check that book, but I think this is the complete answer. Okay. So this is the general answer, where if you take this this is to satisfy the relations like this. Okay, the conjugate. So when you have a relation like this, it's the conjugate will be minus. Yes? Okay. Okay. So to satisfy conjugate commutation relation, which is very important in quantum optics, right? The input and output are related to a phase relationship like this, phase and amplitude relationship. You can see that this place, it has 2 minus sign, yeah, and this has no minus sign. So if you put pi over 2, so it's not like I know it's tempting to say that yes, it looks like this one has a coding on one side, and so it's like the symmetrical one has symmetric codings, and the other one has, the asymmetric one has like coding on one side but not the other side. Yes, I understand it is very tempting to do that, but actually no, they are described by one parameter. So phi, so if phi is, so if the beam splitter imposed a phase shift to the reflected beam, a pi phase shift, a pi over 2 phase, a 90-degree pi phase shift to the reflected beam, then you define, then the phi is pi over 2. If the beam splitter impart no phase shift, okay, so although there is a minus sign here, there is actually no phase shift. No phase shift, okay? So see, if you put it here, you have, and if you put 45 degree, right? So you have 1, 1, 1, 1, and this is I, this is I minus I. Yeah? And this will give you I. But if this is 0, this is 1, this is, no, sorry. This is 1, this is minus 1. You see how this works? Okay. So it's not like physically they correspond to different settings. It is just whether the beam splitter imposed a phase shift to the reflected beam or not. And this question can be answered, it's answered in a paper, which I think the reference is called Hamilton 2000. It's the reference given in Jerry and Knight, and he explained why it has to be this way, like what the physical significance of it, energy conservation, time reversal. So it's all very, very complicated. I know I don't want to go into that. There's no, for our purpose, we don't need to understand that much detail. Okay, so right now I just want to point out that this is not a Hadamard gate. We remember when you apply Hadamard gate twice, it will return to itself, right? So it's like involutory. Hadamard gate is involutory. Involutory. It's really mouthful. Hadamard gate. So if you apply it twice, you get back to the original state. This is very important property in the Deutsch algorithm. Yeah, remember? If you remember. Now, this one, if you do this twice, yeah, what is it? 0 minus 2. So 0 minus 2, 2, 0. So this is 0 minus 1, 1, 0. You see? It doesn't come back to itself. So this wouldn't work. A beam splitter itself cannot work as a Hadamard gate. And it could not work for the Deutsch algorithm because Deutsch algorithm requires a Hadamard gate. So even though the NANU says it's an analog to Hadamard gate and it should work, it won't. Yeah, okay. So what do you need to do to make it a Hadamard gate? What do you need to do to make it a Hadamard gate? What you need to do is to put a pi phase shifter at the port that has a changed sign. Okay? Okay, that's the recipe. Okay. So the other port I just call B prime. So you need to shift the phase of one of them. Okay? If you shift the phase of one of them by pi, which is represented by this matrix, right? Sorry. Yeah? Then you will have this. Okay? Let's do it. 1, 1, 1, minus 1. You see? Okay, this is the Hadamard gate. Get it? All right. So this is how you build a Hadamard gate. You use a very special beam splitter, the symmetric one, and quote, the one that does not impose phase. Okay. It is symmetric physically, but operation-wise, it's asymmetric. And then you put a pi phase shift on the port that is special. Okay, that has on the port that has a minus a pi phase shift with respect to the vertical input beam. Okay, so I understand this all sounds very, very artificial, but that's what quantum computation is. It's an artificial arrangement. Nature does not do quantum computation by itself, except for your brain. Probably your brain is quantum mechanical. I don't know. I would believe that our brain operates quantum mechanically. That's why it's so efficient. Or maybe I'm wrong. But it doesn't matter. Now, we're finally ready to discuss the optical implementations. Okay? Now, what we need to do is to convert this to the optical element that we discussed about. Okay, can we do that? So first, this is the path qubit. Right? You have two paths, horizontal and vertical. And this is the polarization qubit. Yeah? So how do we do path qubit? How do we do for path qubit at Hadamard gate? So say if I have one input and I want to do a Hadamard gate for my path, what physical arrangement should I use? What's the optical element I should use for this path? Beam splitter, yes. And is that sufficient? Okay, if you just want beam splitter, that's fine. Halfway place for polarization qubit. So see, these gates operate on different qubits, so the physical implementation must be different, right? Because the qubit has different nature. One is path-based, and the other is polarization-based. Yeah? Yeah? So for path, how do we realize a Hadamard gate? He says beam splitter. Anybody want, huh?
Glass.
A glass? A piece of glass?
I guess.
For what?
For the time phase.
For the pi phase shift. Well, then you need to you need to have very precise thickness for your glass. Yeah? Okay. But yeah, in principle, it could work. A pi phase shifter. Yes? All right, so that's a Hadamard gate. Okay, remember, beam splitter alone, this is beam splitter. That alone is not sufficient. This is beam splitter plus a pi phase shifter. Okay, so that's that. And this is our function. We will talk about how to do our function later. But how about the polarization port? The polarization port, I asked the input must be 1. So which polarization should I use? Do you remember our convention? Yeah, horizontal is always 1. Just remember horizontal in our path qubit and polarization qubit, horizontal is 1. Okay, so horizontal, and that's 1. Okay, this is polarization. Okay, to do a Hadamard gate for an H polarized state, what do we need? What optical element do we need to use? Halfway plane. And what configuration should we use? Should we take? So this is halfway plane, right? What configuration should we take? It has an angle, right? With respect to the vertical axis. So what is that angle we should set? 2.5? Yeah? Because this rotate this to 45 degree. Okay, good. All right, so we had that. That's great. 2.5. Okay, and then we have the function. And talk about that later. Coming out, I need to use another Hadamard gate, right? On the path qubit. So what should I use? This is like repetitive. I'm repeating myself. Thank you so much for entertaining my very dumb question. Beam splitter plus a pi shifter, pi phase shifter. So this is a Hadamard gate. All right, and then we detect with the photo detector. Okay, and then the other crap. This we don't care. So we don't care its polarization state, right? If we want to measure its polarization state, we could. How do we do that? We could, like for example, measure both. We could, but how do we do that? Huh? HBT. Now we put a polarizer in front of our photo detector. That way we know if the H is coming in, right? Or of course you could use a polarizing beam splitter, which reflect one polarization and transmit the other polarization. You could do that too. Okay, but like at this moment we don't care the polarization state, so we just use a detector that does not distinguish the polarization. Yeah. So this information is disregarded. Okay. So this is how you do it. You first send a horizontal beam to a beam splitter according to this recipe, right? You send a horizontal beam to a beam splitter setting, to a halfway place setting at 22.5, yeah? And then to a beam splitter, and the beam splitter split into two, right? And this port, remember? The reflection from the vertical input, although we don't have any vertical input, but this port is the one that will have a negative sign. So then we will need to put a pi phase shifter. Yeah? So C coming into here become A and B. After the pi phase shifter become A prime. And this become B prime. So let me just B prime, okay? And then you have the mirror, right? Why do you need a mirror? Because later you want to use another beam splitter. So you need to combine the path, right? So here is another beam splitter. So you need to combine the path. And by doing this, you are flipping. Oh, by the way, I didn't say. The mirror itself is an X gate. Yeah, because it flip horizontal to vertical, vertical to horizontal. So a 45-degree mirror is a X gate. You see, all this is definition are kind of trivial. And that's why photonic quantum computing are so easy. They are like one of the first one realized. Okay, and of course, because the optical coherence make all properties of the laser field of the light can all of them can be in superposition. So anyway, so this flip it into a C, right? If flip this into a C and this flip it into a D. And then, so after the beam splitter, you have, remember, a Hadamard gate will have a pi phase shifted for the reflected beam from the vertical input. So again, this is a pi phase shifter. Yeah, so beam splitter, pi phase shifter. And then you measure. Yes? So this is the exact construction of this. Okay, now, so I have given you 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. Okay, we didn't put it here, but that's okay. We didn't put the gate, but it's okay. We didn't draw it here. How about the function? Now the function. The function is this. So depending on the path, you will choose to flip the polarization or not. Okay, so that's how you read this. Depending on the path, you will choose whether to flip the polarization or not. Okay? So that means we need to put in an element, an additional element that represents the function. Okay? And the function, if the function is, and this element will be something that can flip the qubit, flip the polarization qubit. Which is the X gate, right? What is an X gate for polarization state? Louder. At what degree? At what angle? Wrong. Anybody? Yes, 45. Thank you. So if I put it here on path A, right? A halfway play at 45, and I don't put it here, then I have path A equal to 1 and path B equal to 0. Because if I don't put it here, it doesn't flip, so it's 0. If I put it here, it flips, so it's 1, right? 1 plus the input state will flip it, right? Okay, so this is balanced. This is the balanced configuration. And how about constant? Constant will have both take the same value. What does this mean? What does this mean, Tim? Here, constant. What does this mean physically? Huh? No. Here means I put a 45-degree halfway play in the A path, but not the B path. That's what this means, right? Because the 45-degree halfway play flip the polarization qubit. So whichever path I put it in, it will flip the polarization qubit in that path. It's a path-dependent flip, right? So that's this, a path-dependent flip. Okay? So if I put it, if I wanted my balanced constant function like this, what should I do here?
I don't know. You want them to be independent.
No, I want them to be both 1. I want to flip polarization qubit on both paths. What should I do if I want to flip both polarization qubit? What should I do if I want to flip the polarization qubit in both paths?
So you put them on both sides.
Both sides, yes. So you want to put an additional halfway play at 45 degrees. Okay? That's what you do. Yeah? So put in a halfway play at 45 degrees means you take the value of 1. The function takes the value of 1. If you don't put it there, the function takes the value of 0. Okay? All right. So we're almost done. So that's basically it. What you need to do is you try these 2 different configurations and see what you measure here. Right? What do you expect? For constant, this is 1, right? For constant, you should expect to measure. By the way, this could be 1 or both 0. So you can take both out or put both in, okay? But let me just work with these 2 examples. Yeah. Because as we saw last time, right? It doesn't matter which value you take, they give the same result. 1, 0 and 0, 1 also give the same result. In terms of measurement, of course, there will be an overall phase difference, but that will not distinguish the state. Okay, so if you have a constant function set up like this, what do you expect to measure on the horizontal? You expect to measure a photon. But if you use balanced, what do you expect to measure? No photon, but the photon will be found here, right? Yeah. So because Deutsch algorithm works such that if it's a constant function, then the qubit will not change, right? So the output will be 1. 1 is in the horizontal, so therefore you will measure a photon here. But if it's a balanced function, the output will be 0, right? 0 means the vertical, so you'll come out this way. So if you measure a photon here, that means you're detecting 1. Sorry, you're detecting 0. Notice this 0 is the computational basis. It does not mean whether you see a photon or not, whether there's a photon or not, no photon. Okay? In fact, if you want, you could say that this horizontal vertical 1 is defined as 1 photon in the horizontal state and 0 photon in the vertical state, and 0 is defined as 0 photon in the horizontal path and 1 photon in the vertical path. Okay, so it's almost like a 2 photon state. Okay. All right. So let me go through this math rather quickly to show you that this indeed works. Or maybe it doesn't. We'll see. So we are first starting with C. Our initialization is horizontal, and H, right? So we're starting with this state. this 2-qubit state. And the beam splitter and the Hadamard gate, this together will turn C into a superposition. And because it's the horizontal input, not the vertical input, so it is symmetrical. Our halfway plate at 22.5 will turn the horizontal into a superposition too. But in this case, it will be V minus H, right? Because it's a Hadamard gate and this is 1. So 1 will be correspond to asymmetrical, okay? We can work this out like we did last time, and it will be like this. Yeah. So that is what we have here. That's the state here. That's the state here. Okay. I'm dropping the prime. I'm supposed to have prime because the Hadamard gate is really this combination, right? So it's not really A, it's A prime. But well, you know what? I'm just gonna. I could keep that. That's fine. Prime. Okay. Now, let me see. Okay. So the next thing is the function, right? The function. Constant. Let's just try with constant. Let's first try constant. Fa, Fb equal to 1. Constant function. If I have constant function, that means, so this is called 1. That means A prime. I will have A. Sorry. Let me do one more step. Let me apply the function. So after applying the function, this will be Fa prime V Fa prime H B prime Fb prime V Fb prime H. Okay? Yep. All right, now let's discuss the functions. So case 1, constant function. You know, this is kind of boring. So I'm gonna ask 2 people to come up and do it for me. So there are 2 cases. Case 2. Right. No points, but want to do the grace of helping me finish it because it's too boring and I don't want to do it myself. Okay, I see that it's sparking your eyes, so thank you very much for helping, for volunteering. And come on, this is the last lecture.
I just can't do it.
Yeah, I know you missed the last class. How about you? Yeah, I guess also see some leftover spark in your eyes. So you do this, you do the balancing, you do the tungsten. Okay, just like what we did last time. It's not so hard. You have 2 minutes. Otherwise, I can just do it myself. If you are not doing faster than me, 2%.
Oh, I see.
Yeah, that's not
Okay, let me help you.
This might be.
Let me just help. Let me just give you a hint. Here, this is 1. This is 0. Right?
Yeah, but
Okay, and then A, you don't need to care about A. This is 1. This is 0.
so you want to answer to be a function of.
Yeah, just substitute f of. Yeah, just substitute this function values, and then you will see how the polarization state work. Don't forget to convert your 1 and 0 to polarization base. You see what I'm saying? It's V or, I mean, polarization notation. So V and H. And then we were done after this.
What does the plus
It's called sum modular 2. So you add both numbers. So if you have, say, 2 and 3, okay? 2 and 3. What you do is you add these 2 numbers. And you do a modular 2. So that's this, 5, modular 2. And that is 1. Do you understand why? Do you know why? Do you know how modulus work?
What is the same?
Modulus is the remnant.
Why do you have the same answer?
It's a remnant. So this is basically 5 divided by 2 is 2, 1, right? So this remaining number is the modular. Okay. So if you have 4, for example, this remaining number is 0. And this will be 0. So this will only take 2 values, 1 or 0. Okay. All right, thank you guys. That's fast. Okay, you're missing a little parenthesis here, but that's okay. Okay, great. Do you see? What's the difference?
It's just a minus sign.
Yeah. Right? But that's important. Okay, let's quickly check if this is right. So B is 0, so it doesn't change anything. So V, H, they stay. Yeah? And A is 1, so they flip. So this is H, this V flip to H, this H flip to V. That's correct. Thank you. And for this one, both are flipped. So V flip to H, H flip to V, correct. V flip to H, H flip to V, correct? Correct. Thank you very much. Excellent. So there's a minus sign after this operation, right? So in both cases, there's a minus sign after this operation. And now, afterwards, I have mirrors, right? A mirror is what? Is the X gate, right? So the mirror is the X gate. A is converted to horizontal is to vertical. X gate. Yeah? Right? Sorry, I should write this. This is Hadamard gate. And this is X gate. And this is mirror. Hadamard gate is a beam splitter plus pi phase shifter. Okay? And B prime is to convert to C. Okay? So I will write D and C. Yeah? Here I write D minus C. Yes? Okay. Remember the Hadamard gate is reversible, right? So if you see a symmetric superposition, that means after the Hadamard gate will reverse back to so 0 correspond to symmetrical, right? And 1 correspond to asymmetrical. Yeah? So that means this after the Hadamard gate, which is here again, H gate. This one, and of course I can just substitute C and D and then you will see how it works out. But I'm just gonna save some time. So the symmetric combination will get flipped back to 0, and 0 is the vertical. 0 is the vertical. So vertical for us is B. Yep. Yep. And after Hadamard gate, the asymmetrical one will flip to horizontal. Will flip to 1, and 1 corresponds to horizontal. So that's A. Okay? So this is, in the case of balance, you have path A. In the case of constant, you have path B. Okay? And B is 0. Oh gosh. This is wrong. In the case of constant, you have path A. Yeah. Path A. Oh. Oh, wait. Path A is 1. What is wrong here? Path A. Oh. Oh. Sorry, guys. This is 1, right? We made a mistake. So here we should have minus sign. We should have minus sign here. Because the 1 flipped to the asymmetric. Yeah. And this is also 1, right? This is B. Okay, so let me just add minus sign here, minus sign here. And here we have a minus sign. 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 Here we have a minus sign. So this is actually B. And this is A. Okay. You get it? Okay. So with the minus sign, the symmetric one gets flipped to 1, which is A. The symmetric one, so since they have the same sign, get flipped to 0, which is B. So you can see that your input starting with 1, under constant function, it remains 1. So you will detect a photon here if it's a constant function. If it's a balanced function, so that means 1 halfway plane. So not 2, but 1. If that's the balanced configuration. If you do that, then it will flip this, and this is 0. And 0 means you will detect a photon here, but not here. Okay? All right, so that's it. That's the optical implementation of the Deutsch algorithm. Thank you very much for your attention. Today we will we're supposed to have a special we're supposed to have a little special topic on the current research that use NV centers and single photons. And we still have a little time left. So I will skip quiz, and we'll use that time to do this. So I have a few slides, very, very few, 3 actually. And this is just to show you that our this course, the thing that we do in this course is still actively used in current research. And if it's used in current research, you can be sure in 10 years it will still be used in industry. Because whatever we do in research is like at least 10 years ahead of the industry. Okay. Okay. So I want to start with this slide. This is a paper. This is a paper published in 2008 by Jeff Kimball, a man I deeply admire, a modern pioneer in quantum optics. So he wrote this review for Nature. You know what Nature is, right? Okay, so Nature is like the Olympic gold medal in academia. Okay, so he writes, and reviews are invitation only. So it's not like you want to write a review and then you send in your article and they see if they can publish it. No, it's by invitation only. So if they don't invite you, you cannot write it. So Jeff Kimball was invited by Nature to write a review on the status of quantum optics at that time. That's in 2008. That's 17 years ago. Okay, so 17 years ago, what do we know about quantum optics? Actually, we know quite a lot. And he's saying that he envisioned that one day, the different quantum experiment can be connected with a link that transfer quantum information. He called this different experimental site as quantum node. Here, quantum node. And the link that transferred quantum information is we call that quantum channel. Okay? So I wish I have a stick. Yes, there's a stick. Not very glorious, but it will suffice. So between quantum channel, so to get information in or out from a node, you need a quantum interface, right? That's what this represents. This represents how quantum information is converted from something in the node, whatever physical realization this is. This could be an MV center. At that time, maybe at that time there's already MV center. This could be MV center. This could be atomic ensemble. This could be trap ion. This could be super conducting qubit. Okay, so whatever that is, it will interact with photons, and photon will kind of transfer that the quantum state in the box in your quantum node and carry it. It's kind of just because you can. So in quantum mechanics, you cannot clone it. You cannot copy. Okay, there's a theorem called non-clone theorem that shows that you cannot make a copy of a quantum state. So the best you can do is to move it. Okay, you can transfer the quantum state from one type of qubit to another type of qubit. You can map it. Okay, once you map it, the quantum state in the original, so the quantum superposition in the original qubit is gone and is now carried by this new qubit carrier. Okay, so here the channel is typically realized by flying photons, by photons, which is also called the flying qubit. So here is a way that you can map. So this is a unitary transformation. This is how you map the atomic state. Okay, let me just use atom for now. This is how you map the atomic state to a photonic state to transfer the state from one type of qubit to another type of qubit. So that's what this does. And this also could work as a quantum processing operation. So this can contain more than just one turn, right? You can have several turns. One of the turns map transfer the state from the atomic qubit to the photonic qubit. Other transformation does the quantum state processing within the node. Okay, so this is a quantum interface. And on top of that, so this just illustrate physically how you can do it. So this will be an experiment, a cavity, an atom host in a cavity. A cavity is basically a photon trap. So if you trap the photon here and you have an atom in this area, they can interact. Okay, and the study of this system is called cavity QED, and it's fabulous. I love it. But imagine you have a node that does cavity QED and another node that also does cavity QED. What this does is you can. Oh, by the way, in the node there could be some undesired loss or noise. Okay, so that's what this represents. So a node could what a node would serve three functions. We'll have like three things happen to it. One is there will be noise, internal noise or external noise, and there will be also unitary transformation within it, and there will be an interface with the flying qubit, with the quantum channel. Okay, so this is how it works. A single atom, a single photon trapped inside the cavity can interact with the photon based on an external stimulation. So you can turn on the interaction or turn off the interaction based on this additional laser beam. Okay? And in this process, it can also decay. The atom can decay and lost the quantum information. Okay? So here we imagine that we have an excited state first in the atom, and then we use a light to trigger emission to a single photon state, and that single photon state is now trapped in the cavity. And after some time, there's a probability for the single photon state to leak out. Okay, and go through an optical fiber to another node. And when they enter this node, there's also a probability for it to enter into the cavity or be rejected. It's all probabilistic. If they enter into the cavity, it will stay in the cavity for some time. It will not be absorbed until another triggered pulse, another triggered laser pulse, trigger the interaction, turn on the interaction, and it will be absorbed. Okay, so by this configuration, by this construction, you kind of transfer the state from atom 1, excited state from atom 1 to excited state of atom 2. Okay? So that's quantum state transfer. Here is another possibility. You can entangle different nodes. Okay, how do you do that? Well, so instead of feeding your photon to one node, you can beam splitting. You can use a beam splitter to coherently split your single photon state. So you either have 1, 0 or 0, 1. Okay, and it's in the superposition, right? And the node will now not be a cavity setup, but it will just be a vapor, atomic vapor. So it will be a glass cell with hot vapor inside. There will be many, many atoms. That the photon will be absorbed by one of them. But it's uncertain which one of them will be absorbed. So this will be a superposition of all possibilities. If you have like 100 atoms, then there will be 100 possibilities, 100 possibilities, and this will be a superposition for 100 of them. Okay? So if the atom is here, this is in a superposition. If the atom is here, this is in the superposition. So you see that the atom, so we're starting with a superposition of two photons, but we are ending up with entanglements of the two ensembles, right? And then, and again, like here, because it's basically the same atom, same type of atom. So the interaction can be turned on or turned off by a stimulating pulse. So this absorption, you can shine a pulse to it, and then you absorb. And you can store this quantum, this photon, or this excitation inside the ensemble for some time, for however long you want. And during this time, there might be decay. And when you're happy, when you want to use that information, you send in another pulse to stimulate emission of that single photon, and it come out. Okay? And when it come out, it will still remain entangled. Yes? So this works as a quantum memory. Yeah, It works as a quantum memory, and its entanglement also installed. So this is what, and these are all based on experiments that have been demonstrated at that time. So this is what he envisioned that we could have. And after 17 years, people in Netherlands have just published another paper, actually March, so just a few months ago, this year. They published a paper also in Nature where they could use, this is more of a computational science paper, not really a physical paper, but the topic is on quantum network. Okay, and what they do here is they have 2 quantum nodes. Each node contains a single MV center. The experiment we do have an ensemble of MV centers, right? We're dealing with like millions and millions of MV center. But they have only one. So they basically have a microscope that can focus the light down to only a single MV center, and they use a very dilute sample. So you don't have many, and the concentration is very low. So you can find like one isolated MV center easily. And using the microscope, you can find it, and you can focus your excitation to that, your excitation laser, the green light, to that single MV center, and you can manipulate electronic state. Okay. And from the light it emits, you can use a protocol called DCZL. So it's basically a projected entanglement method to entangle these 2 remote MV center. So that's kind of cool. All right, and this paper is shows that they have built a certain computational architecture that could. So basically this, okay? So basically this paper says this has a device-independent programming language that can be applied for different quantum device. So if the quantum device, typically if the quantum device is, say, trap ion, in this is the trap ion. If the quantum device is a trap ion, you need to use certain apparatus, certain setting to make it, to manipulate its quantum states. If it's MV center, you need to use another programming language per se. But this architecture is platform independent. So it's universal, and it can be used to control different. The same setup can be controlled can be used to control trap ion and MV center. So in principle, you can have the trap ion here. You can have this paper is saying that this can be an overlaying architecture on the quantum network that manipulate all different quantum nodes to make them talk to each other. Okay? So just recently, 2025, MV Center. Okay? Another work, not so long ago, this is the basis of this entanglement process. So how do you build this entanglement? It is explained. Actually, this is the same group, I believe. Yeah, Hansen. So this is also from the same group, TU Delft, I believe, in Netherlands. So earlier on, 8 years ago, they have developed this method of entangling 2 remote MV center. And And here they're talking about, we're not doing this in our lab, but they're talking about if you can have a microscope that look at a single MV center, it's likely that you could also find a nearby nuclear spin, a carbon isotope. So carbon usually is 12, right? Carbon 12. It has 12 proton and 12, or no, sorry, you have 6 proton and 6 neutron, right? But you could have carbon isotope that has 6 proton and 7 neutron. And now 1 additional neutron will provide a nuclear spin that can be manipulated. That could either be manipulated or that could disturb. So because this is like a little tiny magnet, like in an NMR. So this nuclear spin is like a tiny magnet, and it could either so typically it is a source of noise. It will disturb, is the magnetic field from this guy will disturb your MV center electronic state. Okay, so it's the source of the coherence. But some people are very smart. They use in this interaction that they have to control the nuclear spin through the electronic spin. I don't know how to do that, but it looks like a very small way to turn your adversary to your friend. Yeah. So anyway, so what they do is they first they take the single photon emission from, remember that 0 photon line? If you remember, in your emission, there is a zero photon line, a very specific frequency that spikes in your emission spectrum. And that line is the photon emission without involving any phonon, side-beam phonons. We could talk about this in our one of our earlier lectures. So they take that 0 phonon, so they filtered out the phonon-related emission, and take that 0 phonon line photon, take the photon correspond to the 0 phonon line frequency. Okay, so that's single photon, and then they combine it and detect. So just like in Humphrey Brown, like in the Humphrey Brown, but here anyway, this is actually like a Hondo-Mandel setup, okay? And when they detect it here or here, they project the state, and then entanglement is produced. So anyway, so after this are entangled. And then they use they take advantage of some of the interaction between the electron spin, the MV center, and the nuclear spin. That is this. Okay. So that is this, and they can kind of transfer the state to the nuclear spin using these operations, 4 gates. Okay. So now, because this was entangled, now they transfer this state to this. Now it becomes the nuclear. Now the nuclear spin now become entangled, right? Because it's the same, just like what we said in the first slide. It's the same state, but just transferred to a different carrier. So if the original qubits are entangled, the new qubit will also be entangled. So this is the state transfer. And then you do this again. You repeat this process, and you entangle this MV centers again, and you do this. You transfer the state. You kind of reinforced. I don't know exactly how this works, because this looks is a little different from this, right? So you see there are 3 gates, and here there are 4 gates. So this is a little different, but somehow you can reinforce the superposition, and the entanglement will be like solidified in a sense. This is called entanglement distillation. So through many cycles, of entangling, you can make the entanglement between the nucleus being very strong. Yeah, and they use and this is the technical base for this, and for them to demonstrate that this architecture works. All right. So this So this very short presentation is not meant to explain everything to you, but it is just to show you that this is what we do in this lab is very relevant to what people do now in research. So even if you want to apply for grad schools, you can apply, topics related to what we do here, and people would be interested in hiring you. Okay, cool. And that's all. Thank you very much for your incredible patience. And that will be the end of our semester.